Okay, so in this video, we are going to discuss what is known as the Jordan-Wigner transformation. So this is a map that it's a transformation that allows us to map spin operators into fermion operators. And why we want to do that? Well, because there may be techniques available for fermions that we can use to better understand our system, and especially when we use this language of fermions, it becomes very easy to distinguish interacting from non-interacting terms. And this is very useful, especially when we are studying these complex many-body systems. Okay, so let's start discussing, explaining this transformation by recalling or defining, if you haven't heard, what we call as spinless fermions. Okay? Because this mapping that I'm telling you will transform or will map spin operators into the operators of spinless fermions. What does that mean? Usually, when we are talking about fermions, now we know that fermions carry spins. And so usually the operator that we use for spins in a lattice is the C, which depends on the site and also on the spin degree of freedom. So this sigma there is indicating the spin degree of freedom. But suppose we are in a scenario or in a case where we have, for example, such a strong magnetic field that all of these fermions have their spins polarized. So the system is completely polarized. So in all sides, let's say, all of these fermions have the spins in the same direction, so polarized. Now, so you see that in this case, this spin degree of freedom becomes not important. It's not relevant. It's frozen. So instead of dealing with this operator, we can just talk about this operator Ci. So what we are saying here is that the Ci with this spin, well, we are just calling it Ci, while the other one, since there is no fermions with this other state for this spin, since we have this extremely strong magnetic field, we can just say that this one does not exist. Okay, so now we are going to be dealing with this operator. So it does not mean that we are talking about a fermion without spin. It does have its spin, but this degree of freedom is not important since all of the particles have exactly the same state for the spins. Okay, so we'll be dealing with this operator for spinless fermions, and as you know, fermions satisfy the anti-commutation relation. So we'll be talking about Ci and Cj dagger will give us, well, anti-commutator means plus here, and this will be 1 if we are talking about the same site. Different sites, these things are independent. This also give us, dependent on the site, this is 0, even if it's on the same site. And the creation operators as well. What does this mean? That Ci dagger squared is 0. This means that we cannot, so this means that we cannot create two, or cannot have two fermions on the same site. And we can also, equivalent, we cannot destroy two fermions from the same site, since we cannot have two. The maximum number of fermions is 1. on each side of these spinless firms. No? So what this thing is basically telling us is the Pauli exclusion principle. No? What these things is telling us is that the number operator can, so this number operator will give us either 0, which means the site is empty, or 1, the site is occupied with a single firm. And so what the spinless fermions tells us is that on each site, we either have one fermion, so it's an occupied site, or no fermion, that's an empty site. So that's what we mean here by spinless fermions. Okay, either we occupy the site or the site is empty. All right, so let's go for the transformation. And so let's go for a transformation that will allow us to move from this language of spins and these commutators that we had for spins. Now let's move into the language of fermions with these commutators, anti-commutators for fermions. How can we do this map? Well, this is the transformation. So, the raising operator in spin, the spin raising operator, will become equivalent, will be mapped into the creation operator for the fermions. But careful, that's not all. Together with that, we have an exponential that carries also an operator, which is the number operator. And it's a sum, where this L, it goes from 1, 2, 3, up to a site before J. So before J, so J minus 1. Okay. Now, the lowering operator for the spin lowering operator will be mapped into the annihilation operator. Okay. But it also has that exponential. And careful now, the sign changes and the order also changes. Now, order matters when we are dealing with operators, and especially when we are dealing with fermions. So again, this L is smaller than J, and here comes our annihilation operator. And if you want to be very careful, you can go on putting hats everywhere. Well, and there is one more spin operator to care about, which is the Z. And the Z is mapped into the number operator with a constant. Okay, so this is the transformation. Let me put it in a box, because that's what we'll be playing with. Okay, and let's apply this transformation to one of these spin half Hamiltonians that we've been playing with. I'm going to apply this transformation into the XXZ model that we talked a lot about, the XXZ model in one dimension for spins half. And I'm going to write it already in terms of lowering and raising spin operators. So then we can directly apply this mapping that we wrote there. So this Hamiltonian for this XXZ model can be written like this. J is the site. I'm going to consider open boundary, so L sites, and my sum goes up to L minus 1. Here we have the coupling strength. And now I'm writing, as you see, in terms of raising and lowering operators. Right? Okay. And on top of that, we have our Z term, the ZZ term, which is here. which you see that we are considering only couplings between neighboring sites. This term is what we were calling flip-flop term, right? And the other one, the ZZ term, is what we were calling the easing interaction. Okay, so now let's map this into spinless fermions. Well, using this transformation, you can see directly that the easing interaction can now be written as that product involving two number operators. Okay, so this is straightforward. Okay, now the other part is the most interesting one. I'm just going to write what we are going to get, okay, and then we are going to study it a little bit more careful. This one becomes J over 2, and we have now the creation annihilation operator showing up, and you will see that we get this term. Okay, but you may wonder, and what happened to all of these sums that we had there? And that's what we are going to work on. Okay, but let me just finish writing this Hamiltonian. So here we have the sum on those sides. And so this is now our Hamiltonian in this language of of fermions. Now it's spinless fermions. Okay, but what we want to clearly understand now is how this was possible. Okay, so I'm going to pick one of these two terms, one of the terms in the flip-flop, and let's analyze it in detail. So I'm going to pick this one. Okay, and let's see. Okay, so using our transformation, S plus J, in our case now is J plus 1, so I'm going to use here the creation operator, and then comes our sum. So the sum is I pi, and that number of operators where this L goes up to J. It's smaller than J plus 1, because here we have J plus 1. Okay, and the other term now, the lowering operator involves the annihilation operator, but here we have that whole exponential, the whole sum in the exponential, where this sum, where this L goes up to J minus 1. Okay. All right, so you see that there are many terms here that will cancel. Most of them will cancel, but one survives. Which one survives? Next from this one, the one that is I pi n j, because this one is not on this sum here. Okay, so the raising and lower the term involving the raising and lowering spin operators becomes now creation and annihilation operator, but in between we have this exponential, which involves also an operator. So this is not a number. And so what happens to that term? And that's the one that we are going to study. We are going to show that this really becomes just that. But let's see how. Okay, so let's isolate here that exponential, and let's analyze it carefully. I'm going to use a Taylor expansion. And so we have I pi, the number operator to the power of m, factorial, where this m goes from 0 to infinity. Well, let's analyze. Well, there are many numbers here, but what we really care is about is the number operator. So let's look what happens to all these powers for the number operator. Okay, so when m is 0, so what I'm analyzing is just this. okay? So when m is 0, okay, we get number 1. So let me put it like this. We get 1 when m is 0. When m is 1, we get just the operator. How about m2? Well, we have this square. But what is this square? What is the number operator? C dagger C, and again C dagger C. Well, for this pair here, I'm going to use the anti-commutator. So what does the anti-commutator tells us? This, correct. So I'm going to substitute this with these terms. So then we get 1 minus C dagger C and C. But that is very nice because now look at this term here. So here we have the C square. And remember, many pages above, C square is 0. We never have a site with more than one fermion. So, very good. We see that the only thing that survives here is C dagger C, which is NJ. So all that to say that when m is equal to 2, let me make this here. When m is equal to 2, we just get NJ. And you can continue with this. If you're going to go to n to the power to 3, well, it's going to be n again. N4 will be n, n5 will be n. And so this is great because now we can come back here and say that from this whole sum, what do we have? Number 1, when m is 1. And for all the others, when m is 1 or anything above, we have the I, pi to m, the m factorial, very good in the sum, but nj for all of them, the number operator for all of these factors of m. Great. So now then, given that, let me copy this and move down. So remember, this is our exponential, no? I, pi, and j is now this. And what is this? Well, this is almost the exponential of I pi. The thing that is missing is the m0 to be really exponential of I pi. No? So exponential of I pi minus the number 1 that is missing in this story. So here we get 1, and then I pi, exponential of I pi minus 1 multiplied by nj, correct? And what is that? Well, I pi is minus 1, so you see that we got 1 minus 2 nj. Okay, so now let's, you may have already forgotten, but let's come back to our original term. And so remember that we were here. We are writing the raising and lowering spin operators in terms of fermion operators. So what we have here, this term became the C dagger. We have here 1 minus 2. There is an operator in this story, the number operator, that came from that exponential. So you see, it was not just a number there. And the annihilation operator. Okay, so these are operators. But the good thing is that we are dealing with fermions. And so this number operator here is C dagger C. And for the same reason that we said before, here we have C square, and C square is 0. And so you see that the only term that will survive is this one, which is our C dagger C. So you see, it was not a simple step. No? There were many steps involved to finally give us this Hamiltonian here. Okay, all right. Now let's study a little bit more this Hamiltonian. And I'm going to copy it below because I want to discuss things in more detail with you. So this is now our Hamiltonian for the spinless fermions. Well, why is it so nice to have the Hamiltonian written like this? Because I can immediately say that this is a term, it's a non-interacting term, while this is an interacting term. And let's discuss this more carefully. Now, we already knew about that because when we are talking about spins, we were calling this one just the flip-flop term, the term that was moving, just the excitations along the chain. And this one, we are calling the easy interaction. So you already knew this distinction, but let's talk about this more carefully. Just let's recall what you may have already learned in the course on quantum mechanics when we are talking about second quantization. Yeah? What we know is that bilinear terms, when we have just one creation, one annihilation operator, for example, a term like this, okay, with some coupling parameter there, a term like this is just does not give us any kind of interaction. A bilinear term like that represents a non-interacting term. A Hamiltonian that involves just terms like this is what we call a quadratic Hamiltonian, because it only has this bilinear terms. A quadratic Hamiltonian is a non-interacting Hamiltonian. Why is this so important? Because they can be solved analytically. These are very simple systems. They are integrable Hamiltonians. Okay, they can be solved analytically. And why? Why we say that bilinear terms like that just indicate non-interacting terms? Because all that we are doing here, well, if this is a hopping term, all that we are doing is taking the particle out of site I and putting it on site J. There is no information about the sites around. There is no information about the particles around. This particle is moving freely. Okay, so it's like a single particle moving freely. If I have this other term on the same site, this is just giving me the occupation or giving me the energy for site I. Again, it has no information about the fermions around, about the particles around. Okay, so these are Hamiltonians that involves only these bilinear terms. These are Hamiltonians that can be easily diagonalized. So these are integrable systems. It's very different from terms. So let me separate these things. It's very different from terms of this kind, which are quartic terms. These terms are indicating real interaction. So these are the terms that we are really interested in. These are indicating really interaction. So they are the terms that we are really interested in these many body systems that we've been studying. These are the terms that add complexity to the system. It's because of terms like that that the system can become chaotic. Okay, so coming back to our um, um, Hamiltonian, this term here is bilinear. It's just hopping. So this is a term of, it's a non-interacting term. Now this is quartic. So what we have here is Cj, Cj, from this number operator, and from this another Cj plus 1, Cj plus 1. So this is quartic term. It's term of interaction. It's term that adds complexity. Now, what is very special for the XXZ model, when we have just spin half, when we are just in one dimension, even though we have this interaction, is a very special model, very particular. It can still be solved through a method. We already discussed this, the Besa-Ansatz method, but very particular Hamiltonian. In general, when we add interactions, we add complexity to the system, we get chaotic systems. Okay, and so why is so interesting to have this description in terms of spinless fermions? Because we immediately can separate. We have bilinear terms, we know it's non-interacting. We have quartic terms, we know it's interacting. When we are dealing directly with the spin Hamiltonian, all of those terms that we saw, we are bilinear. No, it's just two x and y and j. It becomes more difficult to identify or to distinguish which part is interacting, which part is non-interacting. It's true. We analyze these things carefully. You wrote this Hamiltonian, you wrote the Hamiltonian matrix and so on. So you did identify that this was a term of interaction, and this was just our flip-flop. But in general, if you just want to look at the terms and immediately identify what is interacting and what is non-interacting, well, having it in terms of spinless fermions is much easier. And to try to convince you of what I'm saying, let me give you an interesting Hamiltonian for us to think about. Okay, suppose instead of these three directions, x, y, and z, suppose I give to you a Hamiltonian like this, where we have just the xx and the yy. For this part of the neighbors, we already know this is non-interacting. We just saw it. No, it's the bilinear part. Okay, but let me add to this story again xx and yy, but not just involving the neighbors, but involving second neighbors. So if you just look at this Hamiltonian, well, perhaps you're not going to be immediately able to say whether there are interacting terms here. But if you do the Jordan-Wigner transformation, you will. And we'll do this now, but if you do the Jordan-Wigner transformation, you will actually see that this is a very complex Hamiltonian. This is a chaotic Hamiltonian. You can check level statistics and you're going to get a Wigner-Dyson distribution. Okay, so this term here, this one we already investigated above. So now I'm going to concentrate on this other one. Using again raising and lowering operators. Okay, so let's write it. Let's investigate this term, okay, which is contained in this part here, second inversion. All right, so let's use our the mapping that we already found, the transformation. So for the first one, we'll have the creation operator, okay. Then we have that whole exponential, the whole sum in the exponential. And what are the two terms they are going to survive? The j plus 1 and the j, correct? Because all the others will be killed by the exponential that shows up in this other term. So what is going to survive here? I pi n j plus 1 and I pi n j. And here we have the annihilation operator. Okay. Now, this part we already studied above. After we did that Taylor expansion of that exponential, remember that we are dealing with fermions that we cannot have more than one fermion per site. After all that, we found that from here, we only keep Cj. Very good. Well, how about this term now? Aha. If you go through the whole process of expanding that term, what we are going to get, we already saw. We are going to get 1 minus 2n, the number operator. But now this is n j plus 1. Yeah? So you see that now we'll have this hopping term, yes, but we also have this other term, Cj plus 1, Cj plus 1. So what I'm writing here is this guy and Cj. So this is a great term. Yeah, this term here is quartic. It is a term of interaction. Yeah? So you see that if I write this Hamiltonian in the language of spinless fermions, you immediately detect, yes, there is interaction this story. This is a complex system. And in fact, if you study level statistics, you're going to see this is a chaotic system. Okay, so you see now why this is so special. So this is the end of this video.